everyone, it's Coach Fred, and today I'm going to be going over the graph of a log function. But I thought I should remind you what we learned about it Friday regarding the logarithm. So we were trying to figure out what the inverse of an exponential function might be, and we investigated maybe like 2 part 8, and I said to you, we figured out that the heart represented whatever power 2 was raised to get 8. And a lot of you said that the heart would be 3. And I said that that's basically what we're doing with a log function, the logarithm. So I could write this same function as log base 2 of 8. And what that means is 2 to what power gives me 8? Let me write that in words. 2 to what power gives me 8? Now I know it's confusing because it's a word, but it's actually a mathematical symbol, right? It is the inverse of an exponential function. So it's how we undo an exponent. All right, so I could give you, I don't know, log base 2 of 2. So 2 to what power would give you 2? So that would be the number 1. So this is 1. We could do also log base, I don't know, 2 to the 1/2. So 2 to what power would give you 1/2? Hopefully you're saying -1. And then we also learned that log base 2 of, say, -3, if you think about that using the statement, 2 to what power would give you -3, well, there's no power I could raise 2 to that would give me -3, which would mean that this would be undefined. All right, we're going to need that today as we investigate the log graph, okay? So we need to really understand how the graphs of y equals 2 to the x and log base 2 of x equals y are related, okay? Now, I could write this as y equals log base 2 of x as well. They mean the same thing. All right, so let's compare. So because they're inverses of each other, they reflect over the line y equals x, right? We say all inverses are going to reflect over that. For every x, say on y equals 3 to x, there's a point yx on log base 3 of x, okay? So basically what you're realizing is that you're flipping the x's and the y's. All right, but we got to think about this a little bit. So if the exponential function has a horizontal asymptote like this, and we flip the x's and the y's, that means that the logarithm is going to have a vertical asymptote. And so if the domain for an exponential function, which is the x's, is all real numbers, then the log function will have a range of all real numbers. Okay? All right, so again, I really want you to think about how inverses affect each other and how they're related to each other. So let's graph y equals 3 dx. Okay, so first we always want to find our y-intercept. So we plug 0 in. So we can see that 0, 1 is on our graph. We have our equation of our asymptote, which is y equals 0. We want to do another maybe 2 points. So we could say 1, 3. And we could even say 2, 9 if we wanted to. And we could continue to plug points in. All right, so let's think about that. We have this equation of the asymptote here. And we've got the point 0, 1, 1, 3, 2, 9. So we have a nice exponential graph, which is what we were working on this week. Okay, so now if we think about the log graph, that would be, let's be careful here, y equals log base 3 of x. Now let's think about that. If I said to you log base 2 of 2, okay? If you think about it like this, if I set it equal to any variable, okay, that would mean 2 to the a equals 2. That's one way to like evaluate it if you really want to. So 2 to the a equals 2, okay? So we know a is 1. So if you think about it that way, then this is really 3 to the y equals x. 3 to the y equals x. So if you thought about this function and you just flip the x's and the y's, that would be actually what you'd get. But we don't write it like that. Again, we write it using logarithms. Okay, so let's think about this. Instead of having a y-intercept, we're going to be looking for the x-intercept. Now, I certainly could just flip the points around here, but I'd like to try and evaluate it, okay? All right, so we know that the x-intercept has to be 1, 0. Well, let's think about that, okay? If we plugged in 1 for x, we'd have log base 3 of 1, right? So 3 to what power gives me 1? Well, it would be 0, okay? All right, let's try that other point. We know that we can flip it around and it be 3, 1. Well, let's evaluate the log. Log base 3 of 3, right? Because if we flipped it, we know we're going to get 3, 1. 3 to what power gives you 3? The number 1. All right, I hope this is coming together for you now. All right, let's evaluate one more point. The other point, log base 3 of 9, because we know the point 9, 2 has to be on our graph. So log base 3 of 9 is 2, okay? All right, so hopefully you can kind of see that. So what's happening to our asymptote, again, if we flip the x's and the y's, that horizontal asymptote is going to become a vertical asymptote. So x equals 0. All right, so I'm going to try and graph this. So we have 1, 0, 3, 1, 9, 2. And so my graph is going to look like this of the log function. Okay. All right, so let's look at domain and range for a second. Here, let me make this a little bit smaller so you can see all of it. There we go. Okay, so we know that our domain on the exponential function, negative infinity to infinity, and y is greater than 0, so 0 to infinity. So look at the graph now. All of my x values, they have to be greater than 0 because they can't pass that asymptote. So we just flip the domain and the range. And that would be how you graph the log function. Okay, so can this get a little bit harder? It sure can, right? We can shift the graph, okay? So now I have y equals log base 4 of x minus 3. Okay, so I want to show you how to graph this without having to graph the exponential function. All right, so the things that I like to think about are that value, whatever is across from the log, which is not the base, it can never be 0 or less, right? Why? Well, because it's not in the domain of the function. If we look at the graph, it's not in the domain. We need it to be greater than 0. So I always like to think about that graph as I want the value of x minus 3 to be 1. I want it to be 3 or 4, whatever the base is, because then it's a nice pretty number. And then whatever the base is to the power of 2. So in this case, I'd want it to also be 4 squared, which is 16. Okay, so if I think about that, I want that value to be 1. So what would I have to put in? I'd have to put in 4. So I plug in 4. I also want it to be the number 4, so I'm going to plug in 7. I also want it to be 16, so I'm going to plug in, what is that, 19? Yeah. Okay, so if I do that, I'm going to get, if I plug in 4, I'm going to get log base 4 of 4 minus 3, which is 1. We know that 4 to what power equals 1? 4 to the 0 power equals 1. All right, next one. Log base 4 of 7 minus 3 is 4. Why was that a pretty one? Because now I have log base 4 of 4. So 4 to what power gives me 4? It would be 1. All right, last one. Log base 4 of 16, because 19 minus 3 is 16. 4 to what power gives me 16? 2. So I have 4, 0, 7, 1, and then 19, 2, which is like way over here. And so I still have an asymptote, but my asymptote has been shifted to the right 3 units. So I now have an asymptote here at 3, And my graph's going to look like this. Get a blue line. Something like that. Okay, and my domain and my range? Well, my domain is going to be x is greater than 3, right? I want all x's greater than 3, so that would be 3 to infinity. And my range still is going to hit every y on the axis, so negative infinity to infinity. All right, so hopefully that was a helpful video. We're going to be doing some practice of this in class. And have a great night.